Hello everyone, welcome to class number 38 of Physics 218. Last time we talked about the Bohr hydrogen atom. We wrapped up our discussion, looked at energies and spectra and angular momentum quantization. We also started to talk about quantum mechanics in 3D, how you can generalize the time-dependent and time-independent Schrödinger equations to 3D. And we briefly looked at the 3D version of the infinite square well. There were two things that I wanted to remind everyone of. Namely, in 3D, you need three quantum numbers to describe an energy eigenfunction. Also, the issue of degeneracy, that there can be more than one set of quantum numbers that give rise to the same energy eigenvalue. So today we're going to briefly look at the Schrödinger hydrogen atom. We'll talk about the quantum numbers and the energy eigenvalues. We'll talk about angular momentum in the hydrogen atom. And then we'll take a look briefly at the energy eigenfunctions, try to get a little sense of what they look like, and also discuss the probability densities. Our discussion is going to focus on the time-independent Schrödinger equation for hydrogen, which I've written here. We're going to have our hands full just thinking about the energy eigenfunctions and eigenvalues. If we wanted to deal with things like the full time dependence or being in a superposition of energy eigenfunctions, we already do know how to deal with that from everything we did earlier in the semester in 1D, and there's going to be enough here to keep us quite well occupied. So, the goal, is to solve for the energy eigenfunctions and energy eigenvalues. Let me just remind everyone, this term here is our kinetic energy term, where we've replaced the second derivative with respect to x with the Laplacian, and this, is our potential energy term. Okay. So the process of solving this equation is not a straightforward one. One will end up doing separation of variables in spherical coordinates. We're not going to go through the details. I'll leave that for 421. If I were to talk through going through this process, it might take me, I'm going to take a wild guess, 2 classes worth of just straight on talking. So I think we're just going to have to, I'll sort of point out some of the results, but we're going to have to leave the details for another time. So the first thing that I want to mention as we think about the energy eigenvalues, is first to point out that, as you saw in the reading, the eigenfunctions are described by 3 quantum numbers. So I'll write those energy eigenfunctions as psi sub n, l, m, and they're functions of r, theta, and phi in spherical coordinates. Now there's some common terminology here. The quantum number n is typically called the principal quantum number. L is what we call the orbital quantum number, and we'll see why that name is suggestive in a few minutes. And then m is often called the magnetic quantum number. Now you might be wondering what this has to do with magnetism. It is not at all apparent, but it turns out that the behavior of a hydrogen atom in a magnetic field, so that is yet another thing for 421, or maybe even super advanced quantum 470 or a graduate course. But it turns out the behavior in a B field ends up being affected by the M quantum number. One other thing that I should mention is that the notation for this last number is not always m. You'll also see this written as m sub l. So Townsend actually writes m sub l if you go and look at his treatment of this in chapter 6. But I'll sort of stick with Knight and write NLM here. The key takeaway is that just like we saw for the 3D infinite square well, we have 3 quantum numbers in this case. Another important feature is that there are only specific allowed values for these quantum numbers. Now for n, right, we can have n equals 1, 2, 3, or any integer. This seems pretty familiar from 1D quantum mechanics. We saw exactly the same thing when we talked about, when we looked at n for, say, the infinite square well. Where things got a little bit interesting is the other one. So for the orbital quantum number, right? So L can it also goes up by integers, but it can vary between L equals 0, so 1, then dot dot dot, up through n minus 1. Okay. There's also a restriction on m. So m can vary going up from minus L, so minus L plus 1, counting up by integers. Oops, that's a 1. Here, let's 1, dot 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 0, and then all the way through L minus 1 and L. So right, so let's make this clear with an example. So for n equals 1, right, the allowed states we can have are, right, n equals 1, right, because L only goes up to n minus 1, right, L stops at 0 here, and because L can only go up to 0, there's only one possible value for m, namely 0. Things get a little more interesting for n equals 2. Right, so for n equals 2, we likewise have an L equals 0 state. And for that state, the only possible value of m is 0. But we also have a state, or states, with L equals 1. This time, right, with L equals 1, right, we can have m be, we can start at minus L, so we have m equals minus 1. Then going up from there, we have a state that's n equals 2, L equals 1, m equals 0. And finally, n equals 2, L equals 1, and m equals plus 1. Okay, so I think you sort of see how this pattern goes. Just to be sure we're on the same page, let's now have you do a whiteboard exercise where you enumerate all the possible quantum numbers that have n equals 3. And then we'll come back. We come now finally to the energy eigenvalues themselves. So it turns out that the energy eigenvalues look like this. Namely, this is exactly the same as what the Bohr atom model of hydrogen predicts. So, same. So historically, being able to work out the right answer for hydrogen, because remember the Bohr model, right, was believed or was accepted at the time because it made predictions that agreed with experiment. The fact that Schrodinger was able to get the same result was a large part of the reason why he realized he was on the right track in developing quantum mechanics. So notice, right, that this depends on 1 over n squared. I've written the electron mass here as m sub e, so that we don't mix up the electron mass with the quantum number m. Just FYI there. So a few things to notice, right? We pointed out that it's the same answer as the Bohr model gives. So the energies don't depend on L or M. So I've sort of written E sub NLM here to be sort of formal, but very often you'll just see people write E sub N the same way we did like when talking about the Bohr hydrogen atom because of this lack of dependence. Now we saw in the last segment and in the whiteboard exercise that, say for n equals 2, you can have multiple states that have n equals 2, but different values of L or M. This is an example of degeneracy. Right? All of the possible states with the same L, or all energy eigenfunctions, in other words, with same n have the same energy it's abbreviated eigenvalue there. Again, so this having different states with the same energy is something we also saw in the 3D infinite square well.